So last time we saw some application of this regulatory lemma using the embedding lemma. By using embedding lemma, we can actually, find some subgraph in a given graph G satisfying certain condition, which proves, some theorems. We proved the Ehrlich-Stone-Simonovich using the, embedding lemma and regularity lemma, and we also show that the Ramsey number of bounded degree graph is linear in terms of the, size of the given graph, order of the given graph. And now, what we are gonna do is, embedding lemma just, help us to find one copy of a graph inside of, graph G. So one copy of graph, say F inside of G or H inside of G. But by using the, close this. By using the regularity, we can actually, count the number of subgraphs in a given graph. So for example, we can prove this lemma called triangle counting lemma. So let G be a graph, and let's say it has a partition, let's say B. Into 3 vertex set, and Pi and Pj is an epsilon Tij regular pair. For this, I and j between, 1 and 3, and assume that the epsilon is small. We don't even need the epsilon being small here for our statement. Then what we can prove is the number of triangles P1, P2, P3, where P1, Pi is inside of Pi, the large Pi, capital Pi is, roughly as expected, say 10, so what it says is that if we have a P1 and P2 and P3, and if, so assume that these are random graph between, so these edges are there with the, randomly with the probability T1, 2, and these edges are here with probability 1, 3, and these are here with probability 2, 3, T2, 3. In that case, what's the number of triangles? So expected number of triangles is that each P1, P2, P3, this triple forms a triangle with a probability T1, 2 times T1, 3 times T2, 3. Because this edge is here with probability this, and this edge is here with probability this, and this edge is here with probability this, and those 3 events are independent. So you just multiply them. So this is the probability that this triple is actually, this triple is a triangle. And then there are this many triples, and each of them, is there with the probability this. So expected number of triangles is exactly this times this. And what it says is that even if this is not random, as long as this is epsilon regular, then there is some error term, but it's very close to the expectation. The number of triangles in there is very close to the expectation. So I will actually leave this as an exercise. It's not difficult. So you have V1 and V2, V3. how do you count a triangle? You choose one vertex here. The number of ways to choose is this many, but most of them, except a few exceptions, most of them has a correct degree on both sides. So this has t 1, 2 plus minus epsilon times, p too many neighbors, and t 1, 3 plus minus epsilon times p3. And between these two, so this is p1. And if you want to count the triangles, then what do you have to count? You have to find the vertex p2 and vertex p3 such that there is an edge. So you want to count the number of edges between these two sets, and which is, as expected. So you compute that, and then you do that for all the vertices. And for exceptional vertices here, you have to also do something else. Then you will actually, get what we want. So here, there are something slightly tricky that if this set, this set and this set is smaller than epsilon times p2 or epsilon times p3, then you cannot really do anything. But in that case, b13 and b12 are small anyway. So, if those are small, then you can still, prove something along this line. Because this becomes small, so this is not error term anymore. So this is actually dominating this at a certain moment. So you can actually prove this triangle counting lemma. And with this, we can prove this triangle removal lemma. So what it says is that when we have a epsilon positive, then there exists delta such that any n vertex graph with at most delta n cube triangles can be made triangle free. By removing at most epsilon n square edges. So what it means is that when you have a graph G and it has small number of triangles, then it's close to being triangle free. So here close is measured by the, how many edges do you have to remove to become triangle free. Can be made triangle free by removing a few edges. So maybe it seems quite intuitive. If you don't have many triangles, then maybe you can delete one edge from each triangle so that you can become triangle free. Because there are not many triangles, so the number of edges we have to remove might be small. But here, the number of triangles is n cubed, some constant times n cubed. And the number of edges you are allowed to delete is only quadratic. So you can imagine n is much large because we don't have any restriction on n. So n could be much larger than epsilon or delta. So there are so many triangles, so you cannot really delete one edge from each triangle to delete all the triangles. So it's not trivial that you can actually remove only quadratically many edges to make all the triangles go away. So it seems quite intuitive, but it's actually, not easy to prove. No simple proofs are known. except using like heavy tools like regularity lemma or graph limit or other tools. So let's see how one can use the regularity lemma to prove this statement. So we can actually assume that, okay, what we want to do is for given epsilon, we want to find delta, so that if it has less than delta times n cubed triangles, then you can delete n most epsilon n squared to, get the triangle free graph. So we can actually assume that this delta is also small. The epsilon is also small. So if suffice to prove for, say, epsilon smaller than some number, let's say 1 over 1,000. Because if it is true for epsilon smaller than 1 over 1,000, then what you do is you take epsilon, smaller than equal, let's say. Let epsilon be the exactly same as 1 over 1,000. And then for any, so this case you have a delta. There is this delta. And for any epsilon bigger than 1 over 1,000, you just use the same delta here. Then, this is true anyway. You have to remove at most 1 over 1,000 n square when epsilon is bigger than 1 over 1,000. So we might as well just assume that the epsilon is not too big. And let delta be the epsilon to the 4 times power of epsilon to the negative 20 to the negative 3. So remember that the tower is a very big number. So this means 2 to the 2 to the 2 to the 2 to the 2, and this height is about, epsilon to the negative 220. And you take the negative 3, so that means it's 1 over very big number. So this is small number and this is small number, so delta is quite small. So now how we want to do is we want to first apply the regularity lemma. Suppose that we have an n vertex graph G with n most delta times n cubed triangles. And we apply regularity lemma. To obtain say epsilon to the 4 regular partition. So this is our epsilon when we apply the regularity lemma. So we can apply the regularity lemma with the epsilon and t of our choice. So this is our epsilon when we apply the regularity lemma. So we have epsilon to the 4 regular partition V1 to VR, which also satisfy R1 and R2, meaning that this is an equitable partition. Let's say n is satisfied that R is at least epsilon to the negative 4, and at most t, which is power of epsilon to the negative 20. So we take epsilon and t and then apply the regularity lemma. Here our choice is epsilon to the 4 and epsilon to the negative 4. These were our choice of epsilon and t. Then you get this partition, so that the R is at least the epsilon to the negative 4. And now we consider an epsilon to the 4 epsilon reduced graph R of this partition. So recall that this reduced graph R is that when we have a V1, let's write V2, this epsilon regular partition VR, if those pairs are epsilon regular with the density at least, so here in this case epsilon to the 4 regular with the density at least epsilon, then we add an edge between these two. Otherwise we don't. If this is not epsilon regular, then we don't add an edge, or its density is smaller than epsilon, then we don't add an edge. So, sorry, if this is not epsilon to the 4 regular, then we don't add an edge, and if density is smaller than epsilon to epsilon, then we don't add an edge. So that was this reduced graph. If R contains a triangle I, J, K, then what do we have? That means we have Vi and Vj and Vk. And the number of edges between. Yeah, I forgot to mention that we can assume that the n is big. Yeah, because if n is not big, then if n is not big, then since we take the delta small enough, then this actually becomes this 2 number, and we can actually, if n is small, then this may be smaller than that, so then we just delete 1 edge from each triangle, then it's enough. So it's non-trivial only when n is big, so we can assume that n is at least as big as 1 over delta. More precisely epsilon over delta, but basically we can assume that n is big. Anyway, so where were we? So if R contains a triangle IJK, then we have 3 sets such that each of them here and degree is Dij, Djk, density is Dij, here Dik, which are all bigger than epsilon. And all of them are epsilon to the 4 regular. Then by using triangle counting lemma, what do we get? We get that there are at least epsilon cube. So at least let's write it in more detail. At least Dij, Dik, Djk minus 10 times epsilon to the 4, because this is a regularity constant, which is epsilon to the 4. Pi, Pj, Pk. And we know that each of this Ijk is epsilon, so this is epsilon cube minus 10 epsilon 4. But we assume that the epsilon is at least, less than 1 over 1000. So this is actually, epsilon to the 4 times n over r to the 3. Because this is equitable, so these are, we know the size of this. Then what's this? This is actually delta times, bigger than delta times n cubed by our choice. Remember that r is at most size of this tower, and we have epsilon 4 here. So this many triangles. But what have we assumed? We assume that it has at most delta to the n cubed triangles. So this means a contradiction to the assumption. So R, this reduced graph, does not contain a triangle. Now we are gonna clean up the reduced graph R. Meaning that is, we do the following. Now we delete the edges between Pi and Pj, where Ij is not an edge in this reduced graph, where I and j are between 1 and R, where the I and j could be possibly same. That means we delete the following types of edges. If there is an edge inside each Pi, then we delete them. And we delete the edges between Pi and Pj, where this is not an epsilon to the 4 regular pair. And we delete the edges between Pi and Pj, where the density between them is smaller than epsilon. So give me a moment. Yeah. Then how many edges do we delete from each 1 to 3? So from 1 we delete the R under n square, this many edges, which is much smaller than n to the 4 times n square. And because there are R parts, each of them, the R parts, we delete at most R to the n square. So this is at most this. And the second type, how many pairs are there? We know that the epsilon to the 4 times R square. So we invoke the regularity lemma with epsilon to the 4. So this many pairs are not epsilon regular, and each of them could have at most this many edges, because Pi and Pj both have size n over R plus minus 1. So maybe you have to add 1 here, but this is not essential. Then this is at most epsilon to the, again, 2 times epsilon to the 4 n square. And the third type, how many edges do we delete? There are at most R to the 2 pairs, and each pairs you have less than epsilon times n over R square edges. So if you compute this is less than this many edges. So altogether, how many have we deleted? We have deleted at most, let's say less than epsilon n square. Hence, in total, we have deleted at most epsilon n square edges. And now we claim that the resulting graph is triangle free. But if not, if the resulting graph contains a triangle XYG, then how do we know, how does it look like? First, X and Y and G are adjacent each other. So x and y, or two of them, cannot belong to the same partition because we have already deleted all the edges inside of one part, each part. So there should be three parts which contain x and y and g. And then if there is an edge between them, that means this part and this part, these two parts, does not belong to one of these two cases. Otherwise, all the edges between them are gone. That means they are epsilon to the 4 regular with a density bigger than epsilon. Meaning that if this is bi and if this is bj, then ij is inside of this reduced graph. So that means if there is an edge, the triangle xyj, then we can find parts vi, bj, bk such that x is in vi, y is in bj, g is in bk with I, j, k. And this implies that ijk is a triangle in R, which is a contradiction. Because we already have shown that the R doesn't contain a triangle because it has too few triangles. The graph G has too few triangles. So this proves the lemma. So why is it useful? We will consider one application of this triangle removal lemma in the next video.